Welcome to day 17, or day 11 actually. Our homework will be packet page 17. So if you could put that in your planners. Also have your homework out from last class, your descriptions of what we would notice in our tables for linear, quadratic, and exponential. And we're going to pause the video for 2 minutes for you to share those homework answers with someone nearby. As you're taking your things out, we'll also need calculators today, packets, obviously, and a separate sheet of paper. So have your packet out, have your homework out to discuss with a neighbor, have your separate sheet of paper out, and also have a calculator. So actually we'll pause for 3 minutes for you to do all those things, again, including discuss your homework answers with a neighbor. Okay, so in our charts, in the linear chart, we should recognize a constant rate of change column. And that's because our slope is constant in a linear function. In the quadratic chart, we should have noticed a constant second rate of change. So the reason the second rate of change is constant is the first rate of change is linear for a quadratic. Now in calculus, you'll call the rate of change the derivative. So a linear function will have a constant derivative. A quadratic will have a constant second derivative. And then for exponential, the biggest thing that should stand out is that we had constant successive ratios. And those are the big three from our linear, quadratic, and exponential charts that if you didn't know the equation and I just gave you a table of data, you could do some rates of change or successive ratios and pretty quickly figure out what type of equation we would be working with. All right, so this is for your separate sheet of paper. So again, if you could have a separate sheet of paper out as well as your calculator. And what we're going to do with this one, this is kind of a model um, problem that then you'll do one very similar to it on your own in the packet. All right, so we're going to say we have a town has a population of 100 people in 1980, and it grows at 6% each year. Well, whenever you're changing by a percent, that is automatically exponential. So we want to think the basic setup a times b raised to the x. So for our equation, we're going to have y equals our a, like we saw in the bacteria growth, is our starting amount or our initial amount, which in this case would be 100 people. For our b value, when you're working with a percent, you always start with 100%. Since we are growing or increasing, we will add our percent onto that, and this gives us 106%. Well then, our decimal's here right now. To switch that percent to a decimal, we would get 1.06 by moving it over twice. So that becomes our, oops, not 7, 1.06. That becomes our b value, and then we're raised to the x. If we had gone up by, say, 3%, we would end up having 1.03 in there. If we had gone up by 9%, we would have 1.09 in there, and so on. Like we saw with bacteria growth, anytime we write an equation, we should tell what x and y represent. For x, notice we were starting out in 1980. if you have a calendar year that you're starting, for X we'll have years since 1980. And for Y, you can either say it's people or the population. Either of those is okay. So now a couple of follow-up questions. First off, how many people would there be in the year 2000? Well, our years dealt with X. X was years since 1980. Well, the year 2000 is 20 years after 1980. So we'll fill in the 20 for X. Keep in mind, people has to be a whole amount. So we're going to pause the video for 1 minute. See if you can sub that in the calculator, and then round to the nearest whole because it is people. When we sub that in, we should get 320.71 and change. People has to be a whole amount, so the nearest person, this is giving us 321 people. Now, the other follow-up question that could occur is what if they tell us a number of people and we want to find when that would happen? Well, in our equation, notice we said y is equal to people. So we're going to have 300 in for y equals 100 times 1.06 raised to the x. And now we're going to solve for x. First thing we'll want to do is divide both sides by 100. And we'll get 3 equals 1.06 to the x. Now here's the tricky part. If we want to get to an x that's in an exponent, we've got to do a log. In our log, we will have a base, we'll have the inside of our log, and we'll have what it is equal to. The base of your exponent is always the same as the base of your log. The base of our exponent is 1.06. Then the log needs to switch what it's with, or the base needs to switch what it's with. So the 1.06 is currently with the x, now it's going to be with the 3, and then the x goes by itself. So we're going to be putting in the calculator log base 1.06 of 3 equals x. Now the log button is down, it's just to the left of the 1. You'll have to do control first. So we'll give you a moment to type that in and just write out what x is to a couple decimal places for right now. So we'll pause for 1 minute for you to punch that in. And again, keep x out to several decimal places. So we should have ended up getting that x is 18.85 and change. Well, keep in mind that x was years since 1980. So if we're starting in 1980, and it's been 18.85 years, that's going to put us in 1998.85. Well, a calendar year goes the whole year. It doesn't switch till the next calendar year until you get to the next whole. So 1998.85 is probably in like November of 1998. So during what year did this happen? This happened somewhere during the year 1998. Okay, it does not round to the next year because you're still in that 1998 calendar year for the whole year. All right, so in our packets, let's go to page 16 now. So you've got a scenario there. In Townville in 1860, there was 1,500 people. Population grew at a rate of 2.8% per year until 1960. We got to write the equation. Now let's make this t be x, just to be consistent with what we did a second ago. But you're going to write the equation. Make sure to tell what x and y represent using the model that we just did in the last one. Then you got to find what the population is in 1940, and during what year did the population exceed 2,000. So we're going to pause the video for a bit. You're only going to do these three questions. Do not go on to any part of it, any other part of the page. If you get stuck on these three, look back into what we did on the separate paper. If you're still stuck, ask the sub to rewind the video and to replay the part from what we just did that's very similar to the question that you're working on. It should match the A, B, and C that we just did in the last one. So we are going to pause this for about, let's say 12 minutes. If everyone is finished before 12 minutes, we can start the video earlier, but we'll give you 12 minutes to do each of these. Again, make sure you tell what X and Y represent in your equation, and make sure to label your answer in number 2 as well. Okay, so we'll pause for 12 minutes. If everyone's finished before 12 minutes, we can start the video up before then. Alrighty, for our equation, we should have y equals 1,500. For our percent, if we do 100% plus 2.8%, that's going to give us 102.8%. If you move it over 2 spots, that's 1.028. So that's what will be in our parentheses, and we'll raise to the x. Now, as we're going through this, any corrections that you need to make, please make those. X should have been years since 1860. And Y was, you could either have people or population. Either of those is fine. What was the population of Townville in 1940? Well, 1940, that's 80 years after we started in 1860. So we're going to have y equals 1,500 times 1.028 raised to the 80. That's going to give us 13,662.82 and other stuff. So to the nearest whole, we'd have 13,663 people. Again, if you need to correct anything, correct it as you go. When did we exceed 20,000 people? So 20,000 should have went in for Y equals 1,500 times 1.028 raised to the X. We would divide our 1,500 over. And we should have gotten 40/3 for that, is equal to 1.028 raised to the x. From there, we had to switch to our log. Log would have a base that is the same as the base of the exponent, so 1.028. The inside of your log would be the 40/3 and equals x. If you had gotten the 40/3 as a decimal, make sure to keep it out all the way by going up and selecting your previous answer when you put it in your log. And this should have given us 93.79 and change for x. Well, remember we are years since 1860. So if we did 1860 plus 93.79, that's going to give us 1953.79. So therefore, this is going to happen sometime during 1953. So a little bit more than 3/4 of the way through the year 1953, so maybe October or so, is when that would happen. All right, if we move on to part B, in 1960, the growth rate slowed to 1.6% per year. So let's start out by coming up with an equation. So we're going to have y equals, our starting amount should be the population in 1960. Well, they don't directly tell us that. But they told us in scenario A that we are growing at 2.8% all the way until 1960. Well, 1960 is 100 years after 1860. So we can use our equation here to find our population at 1960. So we'll have y equals 1500 times 1.028 raised to the 100. And we'll give you a minute, see if you can punch that in and see what it gives you. And we'll round it to the nearest whole, just like we did the other ones for our people. So we should have gotten 23,736 people to the nearest whole. So that becomes our initial amount in 1960. Now we're going to have something raised to the x. To figure out that something, we're growing by 1.6%. So we're going to have 100% plus 1.6% will give us 101.6%. If we move that over 2, that gives us 1.016. That's what we'll have inside our parenthesis. So this is our equation, but we got to tell what x and y represent. X is now going to be years since 1960, because that was our starting year, and y is again our people. So you should be able to use this equation now to answer both questions 1 and 2. Keep in mind, people has to be to the nearest whole, and make sure to label it with people when you get your answer. So we're going to pause the video for, let's say, 4 minutes. See if you can get your answers for both 1 and 2, making sure to have a label and rounding to the nearest whole. All right, so I'm short on room, so I'm going to write my answer to 1 down here. So we would have y equals 23736 times 1.016. 1990 is 30 years after 1960. And to the nearest whole, we should get 38,214 people. Now for number 2, 2000 would just be subbing in 40, because that's 40 years after 1960. And to the nearest whole, we'd get 44,787 people. All right, let's flip over to the homework. We're going to set that up, and then any time left in the period, you can work with that. So the top 4 here, we want to know if it represents exponential growth or exponential decay. Well, when you have have y equals a times b to the x, you would look at the b value to determine that. If the b is greater than 1, that is growth. If the b is greater than 0 but less than 1, that would be decay. And it'd be growth because when you multiply by more than 1, it makes things bigger. It would be decay because if you multiply by something between 0 and 1, like a decimal or a fraction, that would make things smaller each time. So that's job number 1 on each of those 4. Job number 2 is to find the rate of increase or decrease. Well, let's look at number 2, and we'll do that, find the rate of increase or decrease. So to find what went in here on the last problems, remember we did this. We did 100% plus our rate of increase or decrease to eventually give us what was inside. Well, we're basically working backwards here. 100% plus something is going to equal, and we got to think about what was 4 as a percent before you move the decimals over. Well, remember here, we moved the decimals 2 to the left. So we've got to move the decimal back 2 to the right. If you have 4 and move it back 2 to the right, that's going to be 400%. We want to know what this is, so we'll just call it x. If we subtract the 100% over, that's going to give us that it's 300% increase for our growth rate. So you'll do that on each of the others. You'll do 100 plus equals whatever the current thing is as a percent. Now, the only difference is if you have something less than 1, you'll do 100% minus. So there's one of them here that you'll have to do 100% minus. And then down at the bottom, this is very similar to what we just did. You'll write an equation, tell what x and y represent, and then each of them, after you have the equation, notice each of them then wants you to 5 after 5 years. And they're going to have you round to the nearest whole dollars. So that's your homework, and any time left in the period, you can be working on that, and have a great rest of your day.